Hi guys, welcome back to Data Every Day. Today we're looking at a data set of orthopedic patient data, which has just a number of features, medical features about the patient, and at the end a class either abnormal or normal, and we're going to try to predict whether a patient is exhibiting normal or abnormal conditions. And I'd like to point out that there are two CSV files here, one with a 2-class version and one with a 3-class version. In the 3-class version, we have 3 different labels, which we'll be trying to predict, and I'd like to run predictions on both of them. So this will be sort of a more beginner-friendly video. It's a very simple, nice, clean data set. So let's go ahead and import NumPy and Pandas, standard scalar, and the train test split function from sklearn, just so we can work with the data nicely. Then we're going to use the logistic regression CV model to make our predictions. And for metrics, we will use the confusion matrix and classification report to analyze the results. So I'll go ahead and import those, and then I'm going to load in the data, not just into one data frame, but I'm going to load both of these in. How about df2c for 2-class, and we'll get the 2-class CSV, and we're going to load it in with pandas.readcsv and paste in the file path, and then we'll have df3c for the 3-class CSV. And same thing, but I'm going to get the 3-class file over here, load that in, and let's take a look. Okay, so only 7 rows and only 310 examples, but it's very clean and nice, and I believe the same goes for 3C. If you look at them, you'll notice that the entries are actually identical, and both datasets are identical except for the class label. I mean, there is also the name of this has numeric at the end, but that's just the name. The values are exactly the same. So, what are we going to do? Let's get a little information on each. Sorry, not data. It should be df2c.info. And we can see there are no null values, 310 total entries, and in each column we have 310 non-nulls. There's only one object column, which is the class column. And so it's looking good. Okay, so let's try it with 3C. df3c.info. I'm expecting very similar results. And sure enough, just the same, one object column and no null values. So let's start pre-processing. There's going to be very little pre-processing today, and this should be a short video, but let's just let's do what we have to do. So first let's split the class columns off of the data. So y is going to be just a copy of the class column, but we actually need 2 different y's. We're going to have the y for the 2-class system and y for the 3-class system. So y2c equals df2c subclass, and we'll make a copy. Then y3c is going to be df3c subclass.copy. So we're just taking each column off each respective data set and storing it in a different y. Then our x is just going to be 1x. We don't need to make 2 because it's the same in both data sets. We'll just use the 2c one because it comes first. And we're going to drop the class column to get our x, which will be what we're going to use to predict the y's. Okay, so let's take a look. X looks like just the data without the class column. Y2C is abnormal and normal. And let's just look at the unique values, and we can see we just have 2 classes. And for the 3CY, we should have 3 different. Right. So, I guess the next thing to do is scale X. So by scaling the data, we can help the model. It helps the model if every column takes on a similar range of values. So we're going to scale each column so that it has mean 0 and unit variance. So we're going to create a scalar using the standard scalar from sklearn. And we're going to scale X with the scalar. So we call scalar.fitTransform on X. And that will do it. that'll make sure that every column in X has a mean of 0 and a variance of 1. Okay, so if we look at X now, it's actually not a data frame anymore. Now it's a NumPy array. But if we turn it back into a data frame, it's just the same. I mean, the column names are gone, but you'll see that the values have been scaled so that we don't have these high values like 63 or 40. Now everything is on the same scale. So each column is on takes on most of its values in each column lie between -1 and 1 and is centered at 0. Alright, so now let's split our data into a train and test set. So we're going to train on the train set and then evaluate our model's performance on the unseen test data. So we're going to split using the train test split function from sklearn, and we can split any number of data frames or series just as long as they have the same number of entries, and in this case they do, 310 here and 310 in each of these. So we can pass in x, y2c, and y3c, and it will split them at the same point, and it will also shuffle them for us. So let's include a train size. 70% is pretty standard. We use 70% of the data as train data, and then we'll use the other 30% for testing. And I'm also going to include a random state so that we can reproduce the results. This way we'll always shuffle and split the same way. Okay, and this is going to return 6 different values, a train and test for x, a train and test for y2c, and a train and test for y3c. So we're going to have x train, x test, y2c train, y2c test, y3c train, and y3c test. And now we have those 6 different sets of our data. We're ready to train models. So, let's create 2 models. We're going to need one for the 2 class predictions. Also note that I'm not encoding the labels here. I'm keeping them as text labels because sklearn is okay with that, and it will make it nicer when we use a classification report later to visualize the results instead of just seeing them as numerical labels. If we were using TensorFlow or a different library, we would have to encode them as values from 0 to the number of classes minus 1, but in this case we don't. So 2C, this is the 2C model. In fact, both models are going to be the same. Logistic regression CV model from sklearn. This CV model includes cross-validation capabilities built in, and it also has its own hyperparameter search to optimize the hyperparameters of the model. So we're going to have one for 2C and one for 3C, and they're both the logistic regression CV model. So let's fit them each. Model 2C.fit, we're fitting on the X train, and here we're fitting on Y2C train. Down here, model 3C.fit on X train again, but here it's Y3C train. Okay, so why don't I put a little print. It says models trained. And let us generate the predictions that our models will create on the test set. So I want I want a set of true values and predicted values so that I can compare. Now the true values we already have given by Y2C, and the predicted values are going to be given by model 2C dot predict x test. So these are the predictions given by model 2C. Now you'll notice it's not in the same form. This is a NumPy array, and Y2C is actually a Panda series. So why don't we turn this into a NumPy array as well, so that it just takes on the same sort of format here. Oh, actually this should be Y2C test, right? Okay, so now it's the same. Alright, so let's store this in, we'll call it Y2C true, and we'll store this in Y2C pred for predict. So now we have these two, and we're going to do the same thing for the 3Cs. So all we have to do is change this to 3C, this to 3C, and this to 3C. So now we have a set of true and predictive values for the 2-class model, and a set of true and predictive values for the 3-class model. Alright, now let's get the results. So first let's get the scores. Actually, let's get a let's create confusion matrices and classification reports. So these are some nifty functions from sklearn.metrics. Confusion matrix takes in some true values and some predicted values, and it gives us counts of how many we got right in each column and how many we got wrong in each. Let me. You know what? I'm just going to import some visualization real quick so we can see it. So I'm getting matplotlib.pyplot, and I'm going to import Seaborn. Okay, and now I just want to display this nicely. So let's store this data in CM2C, and I will display it in. We're going to do the same thing for the 3C model, except this is 3C, 3C, 3C. Okay, then I'm going to do a similar thing but I'm not going to do confusion matrices. I'm going to use classification report, which also comes from sklearn. And this will, instead of being CM, we'll call it CLR for classification report. Okay, so now we have our confusion matrices and our classification reports, and now we can display the results down here. So let's split it up. Let's do this. 2-class model results. So for the 2-class model, let's first get the score. Let's print it. Print 2-class accuracy. So we can display it to 2 decimal places and format the string using model2c.score. Why don't I do it up here? Get accuracies. So I'll grab this out of there, and I will just get I'm going to score the test set. I'm going to see how the model performs on the test set and just get an accuracy value. That's what the score will do. So I'm going to pass in, well, actually I should do it under this. Oh wait, no, I don't have to. What did I just do? Okay. So, wait, where's model.score? What happened? Oh, I deleted it? Okay. Alright, so we're going to score it on X test. So the test set is similar to what we're doing with predict, but it's just going to do it, just give us the score instead of create a whole set of predictions. And then Y2C test. And we'll store that in accuracy 2C. Then we'll have the same thing, but accuracy 3C, model 3C.score on X test, Y3C test. Okay, now we can just plug that in. So act2C. And then down here, we can do the 3-class model. So I'll just grab this, paste it in. This becomes 3-class accuracy and act3C. Let's display it to 4 decimal places instead. And you can see we have the same accuracy in both, so it didn't seem to matter. That's very interesting. Okay, we can also print out the confusion matrix. For this, I'm going to use matplotlib and Seaborn to give us a nice confusion matrix. So I'm going to create a new figure with a fig size of 4 by 4, and I'm going to plot a Seaborn heat map, passing in CM2C, right? That's our confusion matrix for the 2-class model. Turning on annotations, I'm going to format it with so that we see it in integer form, and turn off the color bar. Okay, then I'm going to add some label axes so that we can understand more easily what we're looking at. And okay, so we're going to look at the unique values of Y2C one more time. And we want to see the order they come in. So it's abnormal and normal. So I want these to be the x ticks, plt.xticks. Alright, we need to actually specify the locations for them. So I'm going to generate two values, and I'm going to add 0.5. Don't worry too much about that. Then these are the labels. So I believe this should work. Let me just print this out so we can see. I didn't put anything in here. So on the X label, this is the predicted values. And then the same thing's going on the Y ticks. And on the Y label will be the actual values. And we'll give it a title, confusion matrix. I'll say 2-class confusion matrix. Okay, now we have it, we can see it nicely. So a confusion matrix shows us in each category which we got correct, essentially. So these on the X are our predicted values. So you can see that we predicted, of our abnormal predictions, we got 54 of them right and 5 wrong, because it matches up here to the actual predictions. And for our normal predictions, we got 11 wrong and 23 correct. So it looks like we did fairly well. We got very few errors, but we definitely performed better in the abnormal class than in the normal class. Okay, so now this can be applied as well to the 3-class model. Just paste in the same thing. Only thing is I'm going to change this to CM3C, and this is the 3-class confusion matrix. So now we have a 3x3 grid. I'd also like to maybe give it a nicer color map. Mako. Actually, we'll do blues, and I want to set the min. -1. No, 0, sorry. Okay. So just grab that, paste it down here as well. Now this one should look like this, and this one should look like this. Okay. So I have the wrong class labels here. There should be 3 of these, and then we want to get the y3c.unique, and these are our new class labels. So I'm pasting that in here and in here. Alright, I'm going to make the figure bigger since we can't see it now. Okay. Let me delete this as well. Right. Let me just, okay, this is fine. So now we have 3 categories, and you can see our, these are our predicted values and the actual values. You can see out of the hernia category, hernia category, we have 11 correct and 6 wrong, and you can see that most of the ones we got wrong were in the spondylolisthesis category. And out of the spondylolisthesis predictions, we got 23 correct and 9 wrong, and all 9 were in the hernia category. For the normal, we got 43 correct and only 1 wrong, which was in hernia. So last thing to do is maybe just get some classification reports, which gives us just some more information about the confusion matrix, essentially. So let's print out, what was it? CLR2C. Oh, sorry. Not, wait, what? Wait, yes. Why is this crashing on me here? Okay. CLR3C. Let's just rerun the notebook, so it seems to be crashing. Okay. Graph session starting. Alright, let's run all. Shouldn't take too long. Okay, here we go. So this is our classification report for the 2 class model. Precision, recall, and F1 score. This is just sort of giving us information about how well we did in each category. Precision is saying out of all of the predicted values for a given category, how many of them did we get right? So 92% for abnormal, 68% for normal. You can see that here. For abnormal, 92% of our predicted values lie in the correct spot. And here, out of normal, only 68% of the correct values were 68% of the predicted values were correct. For the recall, this is saying out of all the actual values of a given type, how many did we predict correctly? So for abnormal, we have 83%. That's because across this axis, across the actual abnormals, 83% of them were predicted correctly. And for the normal, we have 82%. Right here, you can see 82% of them lie in normal. F1 score is just a combination of the precision and recall. So it's sort of it takes a value between 0 and 1, 1 being if both precision and recall are 1, and 0 being if both precision and recall are 0. Actually, is that true? Let me look up the F1 score formula. Here it is, 2 times precision times recall over precision plus recall. So if either precision or recall is 0, the whole thing goes to 0. All right. Okay, so down here we have a precision of 65 for hernia. That means out of our predicted hernia values, 65% of them are correct. We have a precision of 72 for normal. So out of our normal predicted values, 72% of them. Wait, that can't be right, can it? This doesn't look right. Doesn't this not make sense? Because maybe these are flipped. Oh, they are. They are, and I may have... Yeah, I flipped them. Okay, I'm sorry. You can see the order is actually here, hernia, normal, spondylolisthesis. So these need to be flipped. Like that. Okay, now it makes sense. So out of our hernia, precision is 65 because 65% of them of this column lie here. Normal, 72% because 72% of our predicted values lie in the normal category, and 98 on the spondylolisthesis because 98% of them lie here out of these 3. So recall is across this way. Out of the actual values, how many did we get correct? 58% of them in hernia, right? 77% of them in normal, and 98% of them in spondylolisthesis. So it looks like the spondylolisthesis category we did our best in. Yeah, and our worst category was the hernia. Well, very interesting. Okay, this was meant to be just sort of like a basic video. It actually ran a little longer than I meant for it to, but that will sum up today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.